Definitely should. How'd you take that guy's derivative? Good. What's the outside? No. What's inside of something else? All right, so my question really is, what's the difference between those two notations? That is a shortcut way to write what this really is. This is sine of x squared. So what's the inside function? X squared. It's inside the what? The sine. This is really a shortcut way of writing that. So how would I take this guy's derivative? What's the outside function? Sine. So what's the derivative of sine? Cosine of stuff. And then the stuff gets a turn. What's the derivative of the inside? So this y prime would be 2x cosine x squared. What about this guy? What's the outside function now? The squared. So how do you do something squared? Squared. Yeah, bring the 2 down. Times the derivative of the inside. And what's the derivative of sine? Cosine. What's 2 sine x cosine x? Yeah, sine 2x. Neato. Oh, that's the identity you need to know, right? Sine 2x is 2 sine x cosine x. It's really just sine of x plus x, and then you use the addition formula for sine. Okay, so just like we did tangent a minute ago, I want you guys to do, let's do secant. Figure out that guy's derivative. Where secant is 1 over cosine. I love it. S goes to C, C goes to S. To be honest, I would not use quotient rule when the top and bottom is a constant. Screw that, because then his derivative is 0. It doesn't really contribute anything. I would write it like that. All right, so I need to take this guy's derivative. I need to do the derivative of something to the -1. Yeah, the -1 power comes down in front of the thing, and the thing is now to -2. And then the thing gets a turn. Because derivative of cosine is negative sine. So I get negatives positive. I get sine x over cosine squared x. Can we write that a little better? What's sine over cosine? Tangent. And what's 1 over cosine? Secant. So it becomes secant x tangent x. So the derivative of secant is secant tangent. Freak it out. Okay. How are you guys doing so far? So once you learn, so this is how we're getting away from limit definition of stuff. We build up some basic functions, we build up some derivative rules, and then together we can build up other functions derivatives without having to go back to the limit definition. My God, I wouldn't want to do secant of x plus h minus secant x over h. Right? That's reduction. I wouldn't want to do it. So this is much better. We already built up cosine's derivative. I have the rules needed to do this. Beautiful. I love it. So here's what's really cool. Sine x is, derivative is cosine. Cosine's derivative is negative sine. All the co stuff turns out to be negative. Kind of nifty. So watch this. This is kind of cool. Without going through the whole derivation, the derivative of tangent was what again? Secant squared. The derivative of cotangent, this is kind of cool. We could do the whole thing we did with tangent, but let's just, the derivative of cotangent turns out to be negative because it's cosecant. So it's negative cosecant squared. And again, you can do the same thing we did. Make cotangent cosine over sine. Do the quotient rule, right? And then what's the only one that we haven't done yet? Cosecant. So what do you guys think cosecant's derivative would be? So secant's derivative is secant tangent. I'll bet you anything that cosecant is secant tangent. I bet you cosecant is cosecant. Cotangent with a negative. Remember, cos stuff is negative. Yeah. It's almost too nice to believe in terms of memorization, which is what you need to do. You need to know these. Kicks ass. So derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared. Co stuff becomes a negative derivative. I like it. I like it. Let's revisit something we did earlier this summer, last week. So we got what they want from up here? No? What do you mean? What's up?
What? Oh, sorry.
You got what you need? I was like, you're over there like, no. On board it. So the derivative of b to the x. We actually felt that out a little bit. I want to prove this. And you have to use something that people forget about. What we're about to do comes up every now and again in calculus and other math classes. It's remarkably useful. What is e to the natural log of b? It's b. Why? Because e and natural log are inverses, so when you raise e to the natural log, they kill each other. So I can rewrite this as e to the ln b times x. Because it would be, all right, let me go step by step. This would just be e to the ln b to the x. And of course, what do you do with the powers? You multiply. I had a few people looking at me like, you just went crazy, Jeff, but just have to deal with it. Now, how do I take this guy's derivative? I used what? How do I take this guy's derivative? Chain rule. So if I do this guy's derivative, y prime, e to anything is itself, and then the inside gets a turn. What's the derivative of x ln b? What's the derivative of 7x? 7. What's the derivative of 2x? 2. What's the derivative of ln bx? ln b, because ln b is just a number. right? B is just some base. And remember, what was this? This was b to the x. So b to the x ln b, you guys remember that? Yeah, that's what we got before. So 2 to the x would be 2 to the x ln 2. This is definitely a bit more of a proof than what we did before. It was sort of feeling it out, what we did before. Okay, I like it. This is one of the more obscure derivative rules. People tend to forget this pretty quickly, but it's relatively simple to remember because E is the one, that's why E is its own derivative, because ln E is the only thing that's 1, right? ln of E is 1. Okay. So, let's do this. Let's do... Yeah, okay. Let's do some more of these. Yeah. Find all locations of horizontal tangent lines for f of x equal 3x minus 7 to the 5th power, 4x plus 1 to the 7th power. Try to start catching up to you guys. It's the problem that destroys Math 178 students because they very often have completely forgotten how to factor anything. Might describe some of you guys have. So if I start to do this GI's derivative, this is primarily a what? What rule rules this? What rules the most? Product rule. It's a product. So derivative of this one times that one. So let me just write down what the rule says to do. Take the derivative of this one times that one plus, leave this one alone, derivative of this one. All right, so then how do I take this guy's derivative? Yeah, bring down the 5 times 3x minus 7 to the 4. Times 3, good. Times the derivative of the inside, times 3, times this business here, plus, leave this guy alone, I take the derivative of that guy. You bring down the 7. 4x plus 1 to the 6th times the derivative of the inside, 4. I like it. I have to switch to that. Let's see. See if any of these can hold out. Let's see. So this is 15 times 3x minus 7 to the 4th times 4x plus 1 to the 7th plus 28 3x minus 7 to the 5th 4x plus 1 to the 6th. I'm trying to find the location of all the horizontal tangent lines. So what do I have to do with this? So you kind of gave it away earlier. So that equal to 0, and then I have to factor it, right? I don't know. Something plus something equals 0. There's an infinite number of things that could be. I've got to factor it to force it to have a 0 property, right? The 0 product property business. So what can come out of here? No numbers can come out of here. Let's see. How many? 3x minus 7 is going to take out 4 of them. And that can take out 6 of those. So I take 4 of these and 6 of these. So that leaves me with 15 times one of these left. Right, so I get 60x plus 15. And then I took all of these guys out of that guy, but I left one of these 3x minus 7, so I get plus, oh, what is that, 84x minus, oh, scheisse, 140, 196, is that right? Yeah. Just distributing the 28 through the 3x minus 7 that's left. So then I get 3x minus 7 to the 4, 4x plus 1 to the 6, and then I get 144 x minus 181. Is everybody cool with what just happened? Or what's up?
What just happened?
So I can take 4 of these out, right? Because he can get 5, but he can only get 4. I can take 6 of these out because of him. If I try to take more than 6, he's going to freak, right? So I just call that like the at least not evil tax man. Okay, I'm going to take more than you got, but I'm going to take all you got. And then what's left of this first piece then? 15 and a 4x plus 1. Because I only took 6 of those. So 15 times 4x plus 1, bam. And what's left in this next guy? One of these 3x minus 7s and the 28. So then I multiply 28 through the remaining 3x minus 7. Okay, so then I get, where are these horizontal tangent lines going to be then? They're going to be 1 at x equal to 7 over 3. It's going to be 1 at x equal to 2, negative 1/4. And there's going to be 1 at 181 over 144. Those are the 3 locations of the horizontal tangent lines. Okay. So that's a very standard process. This is why when students realize that you have to be careful with how you put something together for it to be factorable. If I just threw up here without even thinking some polynomial, more than likely it's not going to be perfectly factorable, right? But so many processes in the natural world and in economics, which is completely not natural, so many of them follow these rates of change that start with these kind of things. And then you have to be able to factor it to get somewhere. I like it. All right. So factoring is out there. You guys all cool with that? You guys semi-decent with that? So nothing really majorly different about that problem. It's just got a lot of shit going on. Okay. What was the other thing? Oh, oh, let's do this real quick. See if this is any good at all. If I write this like this, now obviously this is, what is this actually? X to the sixth. And what's its derivative? Yeah. I like it. So if I write it any different way that is still x to the sixth, its derivative better still be the same damn thing. So I often show students, if you think the derivative is just going to be this, it doesn't make any sense because that's just going to be 3x to the fourth, which is not what it's supposed to be. What is it missing? So watch this. This is 3x to the fourth. Is everybody cool with that? That can't be right because we know that's the right answer. What is this missing? A factor of what? Which is exactly the derivative of the inside. So that's another kind of, it's not a proof, but it's motivation as to why the chain rule works. It gives you what you're missing. So this should be times the derivative of the inside, and then that would be 6x, 4x, x to the fourth. I like it. I like it. Somebody's out of the audience. What are you, Jeff? All right, let's check. All right. There's something else I feel like I'm forgetting about this section, but oh, that's right. That's right. Okay, perfect. This is chain rule 3-4. This is from a earlier section, this idea, but well, actually it's from this section too. We just said this earlier. What's sine 2 theta? What's another way you can write that? We just said it earlier. I'll start us off. 2. Okay. Maybe I should have a trig identity quiz tomorrow. Would that force you guys to do what you got to do to get ready for the test? You guys think it's evil when actually it's nice? There's going to be some of this shit running around in the test. You just got to know how to do it. What is sine 2 theta? No, sine 2 theta can't equal cosine 2 theta. That wouldn't make any sense, right? There's only certain places where sine equals cosine. We just said this earlier, I thought. 2 sine theta, cosine. All right, well, that was supposed to be the easy step. That's writing that down. Now watch. If you took the derivative of both sides, let's just try this out. And this is something we're going to do very soon. So I wanted to make sense as to why we're allowed to do this. In fact, we always do that. What I do to this side, from here to here, what I do? On this side, what did I do? I took the derivatives. And what did I do to the other side? Took the derivative. So, of course, whatever you do to one side, you got to do to the other side. So here, it's not y equals something, it's sine 2 theta equals, it's a trig identity. But if I take the derivative of one side, I can take the derivative of the other side, and I'm going to end up with a different identity. Sometimes a very stupid one like 0 equals 0. Thanks, derivatives. But let's see what happens here. I take the derivative of sine 2 theta. What's the inside function? 2 theta. What's the outside function? Sine. So how do you take its derivative? Derivative of sine is? Cosine. And derivative of the inside function is? 2. Are you all freaking out about theta? Is that maybe? Theta is just a variable like x. Who cares? You guys are all just freaking out about derivatives. Okay. How do I take the derivative of this? What's the main thing happening on this side? Product. I love it. For some reason, do I have to take, is 2 a functional part of this? No. It just comes for the ride. If you did do the derivative of 2, what's the derivative of 2? 0. It's a flat line. It's got no slope. So that wouldn't even show up. So I really just have 2. Now how do I do this? Derivative of sine is cosine times another cosine is cosine squared. Plus, we'll start with a plus. 2 sine, what's the derivative of cosine? Yeah, negative sine. And then if I divide both sides by 2, I get the identity for cosine of 2 theta, which is the one that people more often forget, not the other one. So you get cosine 2 theta is cosine squared theta minus sine squared theta. That's the identity for cosine 2 theta. I love you guys. And the crowd goes, yeah. All right, Jeff, whatever. All right, that's kind of nifty. You could try that out on other identities. See if they actually become identities, other identities. It's another way to memorize less shit. Okay. And of course, this is the guy that has multiple ways because cosine squared is, for example, 1 minus sine squared, so then you get 1 minus 2 sine squared. Or sine squared is 1 minus cosine squared, so then you get 2 cosine squared minus 1. There's 3 different ways to do that one. Oh, I got a lot of interesting looks on that one. Okay. Okay, I think that was the other thing I was thinking about. Yes. I like it. Okay. So a little bit of, make sure there's something still in my brain. I think every now and again. Oh, let's do this. Let's do this. Okay. Let me bring higher level derivatives into play. Everybody understand the question? What am I asking for? Third derivative. Yeah, so prime, double prime, triple prime. Just keep on taking derivatives until you get to the one I need. catch up, you guys. Ready for y prime. I take the derivative of this guy. What have you guys been doing? You know, he said something about drawing a duck, Jeff. I just did that.
So it's
Yeah. The sine is cosine. Drew, the inside function is 2. So this will be 8 cosine 2 theta. And what happens here? Yeah, so it's minus, now the derivative of e to the negative 2x is itself times the derivative of the inside, right? So let me write this out step by step. So it's minus, derivative of e is the same thing. What's the derivative of the inside function? So that becomes, y prime becomes 8 cosine 2 theta plus 2e to the negative 2x. So what's the second derivative? It's going to be very similar. You guys kind of see how this is going to be 16? Yeah, so negative 16 sine. And every time you do this, you're just going to get another factor of negative 2. Do you see that? Because e is going to be itself, and then the negative 2 is from the chain rule piece. So now it's going to become minus 4. So then y triple prime. Yeah, exactly. Sine becomes cosine, and then double that, so it'll be negative 32 cosine 2 theta. And this is going to get another factor, negative 2. And let's see. Now higher derivatives than 3, you don't just keep doing the little tick mark. Oh my God, we go insane for the 32nd derivative. Let me count this. So we just do this kind of thing. If I want the 4th derivative to be y4. So somebody help me out. I want to know y7. No. I don't want you to do y5, y4, y5, y6, y7. Can we tease it out from what we see happening? Look. 4, 8, 16, 32. Right, and how many more times do I have to double it? 4th, 5th, 6th, 7th. 4 more times, right? You can start to see the patterns. Yes, no, maybe so? And you see how it's sine, cosine, negative cosine, sine, cosine, negative cosine, right? So what's it going to be? So sine, cosine, negative sine, negative cosine, right? So now it's going to be, for the 4th one, it'll be sine, cosine, negative sine, negative cosine. All right, so it's going to be, I know it's going to be negative, I know it's going to be cosine. So you got to double this, 4th, 5th, 6th, 7th, so it'll be 64, 128, 256, 512. So cosine and sine, cosine, and e are very similar in that respect. They are cyclic in a way. Now, e is not truly cyclic; it just kind of builds. Right? But sine and cosine, it makes sense that they're cyclic. Their graphs are cyclic. This one is going to be what? So this is 1, 2, 4, 8. I got to double it again. 4, 5, 6, 7. It's going to be 16, 32, 64. 128. Will it be positive or negative? Yeah, because on every odd one, it's positive. So the 7th is going to be positive. Anyway, so there are some problems every now and then in the book. They ask you to figure out what is the nth derivative. So you do the first couple, first maybe 3, and you try to see the pattern, and then you build it off of there. It's got to be some kind of easy pattern, and that's why they're asking you the nth derivative. Okay, I like it. Okay, and then, oh, yeah, those are pretty simple. Here, before I get too far away from stuff. All right, let's see if I can work. All right. Be interesting. Oh yeah. Let's see. Oh yeah. Kind of curious on this first one if anyone did something before they started doing derivatives. So if you wanted to, you can multiply top and bottom by x. So you get x cubed minus 1 over 4x minus x squared. You wouldn't have a negative power. So it's sort of like clearing the fraction inside of a fraction. This really is 1 over x. All right. So a lot of times, some parts of calculus are all about what are you aware of that you could do. So if I ask you to take the derivative of some function, there's something that can simplify that function, I'll show you do that, because then it'll make the derivatives easier sometimes to do. Well, let's just see what this looks like directly. How would you do the derivative? Start me off. You got 2x. Good. Plus x to the negative 2 times the bottom. I like it. Minus. And leave the top alone. Derivative of the bottom is just. The derivative of the bottom is just. What's the derivative of the bottom? 1. What's the derivative of the bottom? Negative 1. Right? Again, it's when I ask you what's the derivative, it's really asking what the slope is. So if it's a straight line, it's the number answer. It's the slope. mx plus b, the slope is negative 1. All over 4 minus x squared. I like it. Yeah. And I just clean it up a little bit. All right, so now I gotta distribute that. So I'll get 8x minus 2x squared plus 4x negative 2 minus x to the negative 1. Let's see, this becomes plus x squared minus x to the negative 1 over 1 minus x squared. That's still taping, right?
Mhm.
Good. So then I get, what do I get here? I don't have any other x terms, do I? No. 8x minus x squared plus 4x negative 2 minus 2x negative 1 all over this business here. Yummy. Now, if you would have multiplied top and bottom by x, you would get the same answer, just in a bit of a different form. All right, so everybody cool with that one? Is that all right? Yes?
Is it okay to just move the top x down?
No.
Huh?
It's because it's minus that.
Okay.
So if you move it down, this is only being divided by it, when before it was being subtracted by it, yeah. If it was a factor at the top, then it can move down. Okay, I like it. What about this guy? Should be 2. The first thing I would do is to rewrite the inside as 3x to the 1/2. The really funny thing to me is I wish we had never come up with the root symbol. It's completely unnecessary. Square root x is x to the 1/2. And to be honest, this is the more useful thing. It's just that you normally learn this symbol first, and then you learn this symbol and you go, oh my god, why do you use the 1/2? It should be the other freaking way around. Actually, it should be just screw this shit. Yes, I love that. Some of you guys, I know you're just like, there he goes again. It's all funny. This part of math sucks. I'm like, whatever, Jeff. I think it all sucks, so we agree somewhat. So, what's the derivative of the outside here? Say again?
Secant squared.
Secant squared? Secant squared of stuff. And then the stuff gets a turn. What's the derivative of the stuff? See?
3/2.
Yeah, 3/2 x to the
-1.
negative 1/2. Whoa. So I just get 3 secant squared 3x to the 1/2 over 2x to the 1/2. Sure. Is that cool? It's only good to rewrite it with all the negative powers, positive, flip those suckers. Put the tops and bottoms of fractions on the top and the bottom of the stuff. I mean, it's just a little bit more concise way.
That says 3 times the square root of x in the original problem. It's like tangent of 3 times the square root of x.
Yeah, it's 3 times the square root of x, yeah. I'm sorry, it's not a cube root.
Okay, yeah.
Yeah, the cube root, I try to sit him in there. My bad. So if you did it as a cube root, I understand. Finally, this dude here. Now this one freaks people out because the derivative of secant is weird, right? So a chain rule with derivative of secant gets a little bit strange. And another thing is, I often have people think that this is a product rule. But SCC by itself doesn't mean shit. It's got to be secant of something. So this is all day a chain rule. That's inside of secant. Is that cool? So this will be, the derivative is going to be, what's the derivative of secant of stuff? Secant stuff, tangent stuff. And of course, you multiply that by so that's the derivative of the outside. I'll take the derivative of the inside. So the derivative of E is e to the cosine x. And then cosine x gets a turn. Yep. So negative. Sorry, I just put a negative way the hell out there. I'm not going to make an after-class poker session. Yes?
E to the cosine x.
E to the cosine x. Yeah? E to the cosine x times negative sine x. Is that cool? What's up?
Yeah.
Yeah.
Never mind.
Okay. All right. So again, let me show you. If you are uncomfortable with, rules, so when I did that y equals tangent 3x to the 1/2. When you do the derivative, you can say, okay, secant squared 3x to the 1/2 times the derivative of 3x to the 1/2, and then you can focus your attention on that piece. You don't have to try to do it all in your head at once. You write the rule, then you apply the rule, or you do the derivatives. So I often say the derivative is the second step if you're not really comfortable with this stuff. The rule says derivative of the outside times the derivative of the inside. All right, now in the next step, we're going to worry about this, if you need to. Now, I think what we have a couple more things to talk about, but real quick, what I think we're going to do tomorrow is bring here sort of like, I'm going to call it like a group quiz, but I'm not really going to grade it. I'm going to bring some for you guys. It's going to cover basically everything we've done in 3 so far. Before we get into section 3.5, 3.5 is normally a bit of an interesting, we'll see. It's something called implicit differentiation, which, oh shit, okay, there's your reaction.